So far I've discussed line integrals with respect to arc length, and I just want to mention that there is another version of line integrals that is sometimes used, and they get used more when we start talking about vector fields, which we're not up to yet. But I want to mention them now. So you can also do line integrals with respect to one of the variables, either x or y or z. So let me explain this. So we've been doing with respect to arc length. So we have a function, let's say 2 variables, and we're integrating over some curve in 2D space. So it's a one-dimensional curve in 2D space. That's what makes it a line integral. And it's with respect to arc length. Okay, and we learned that the practical way to actually calculate this is to get a parameterization for c, and then just turn everything into the parameter t. So it looks like this. Okay, and this square root came from working out arc length, making a little right triangle. That's where that came from, Pythagorean theorem. All right, but we could also weight our line integral, instead of with respect to arc length, we could just weight it with respect to, say, x or y in this case. So sort of only weight it by the horizontal nature of the curve. And I know that seems just arbitrary and weird, and in general we don't do that too much on its own, but as I say, it's going to come up for vector fields for us in a little bit. So if you can just bear with me, I'm just going to explain how it works, and later on we'll see it come up in a more natural way. Yeah, so this actually is a little bit easier, because all we have to do here, again, we need a parameterization for c. We need an x of t and a y of t. We sub those into our function. And then what I'm going to do is, instead of, I don't have to do a whole Pythagorean theorem thing, I'm just going to, well, here, I'll just do it right here. Take my dx, I'm going to divide by dt, and then multiply by dt, and of course that's fine, I haven't changed anything. And this dx dt is just a single derivative that I can get from my parameterization. And then dt, then this just says integrate with respect to t, and a to b. So instead of having a square root of a combination of the two derivatives, I just simply have one derivative and no square root at all. If I were doing the line integral with respect to y, it would be a similar thing, only I would say dy dt dt. So I would just put the single y derivative in there. Okay, and if this were a function of 3 variables, x, y, and z, and I was doing a line integral in space, then I could do a dx line integral, a dy line integral, or a dz line integral. I think you can generalize yourself. I won't write it down, but you get the idea. Okay, so as I say, in general, these are actually typically a little bit easier to compute because you don't have a square root. You just have to multiply by the corresponding derivative. And you know, it's of course could still be tricky, a tricky antiderivative to do, or even an impossible antiderivative to do, depending on how complicated each of these is. But it's going to be, you have a better chance of being able to do it than this one with the square root. But as I always want to remind students, you can, if you ever get stuck, you could always fall back on doing it numerically, which your calculator can do, or you could even do by hand in a pinch. All right, so that's this is a additional version of line integral that will come up when we hit vector fields, and I just wanted to show that to you at this point.